Okay, today we are going to be covering section 30-4, photon scattering and the Compton effect. And I promise this one will be shorter than yesterday's notes, which I know got a little lengthy, and I apologize, they're more boring even than usual probably. However, today we are going to start by talking about, again, the energy of a photon, which we are given by the expression E equals hf. It's becoming a very familiar equation for us. The new one, however, is that we can also calculate the momentum of a photon. And in this case, our momentum, which is the lowercase p, is equal to hf divided by the speed of light. Or, if we simplify the expression further, it's h divided by the wavelength lambda. And you can use either of these two expressions in solving for the momentum. It's based purely on the information that you are given within the problem as to which one you might choose to use for that. These are both going to be important characteristics that we can calculate. The energy related to the frequency is obviously one we've been doing for a few sections now. The momentum might be a newer one, but it's fairly easy to pick up on, seeing as all of those variables are still the same ones you're associated with. H is still Planck's constant, F is still the frequency, and C is still the speed of light, and lambda, of course, represents the wavelength. So there's not much new on that front as far as the letters and symbols go. So we'll jump right into the Compton effect then. And for the Compton effect, what this describes is that if we have a photon of light that is coming towards an electron, which we traditionally think of as a particle, and the photon of light more traditionally maybe as a wave, but now we are thinking of this as a quantized energy packet of light coming towards our electron, and the electron is going to start at rest. So initially it's not moving, it's just sitting there, and this photon, which represents an X-ray, will be coming in towards it. This X-ray has a certain frequency that it will start with originally, and from there, after it scatters, it's going to change. So the photon will actually collide with the electron, and it's kind of like an elastic collision that we talked about with momentum. And so if we compare it back to the straight line that lines up with the direction the photon originally was coming in at, the photon will get scattered in a certain direction, and it will now have a new frequency. It will lose some of its energy, and since energy is equal to h times f, h is a constant, so f has to change. This angle will relate to the amount that that energy changes, and then of course we have to have things balanced, so that means our electron over here would now be moving off in a different direction as well. The angle that we're going to be concerned about is this angle, the new angle of the new direction for the photon after it has been scattered by the electron. And so that's what's going to show up in our equation in a short while here. A few things to note from this. First of all, the energy for the incident photon is going to be equal to the energy of the photon after it's been scattered and also you would add to that the energy, which is now kinetic energy, of the electron as it has now been also pushed off in a different direction. So what we have here is really a relationship that is showing us again the conservation of energy. And if we put that into the equations that we have, or use the equations to formulate a new one, hf would represent the initial energy. The new energy for the scattered photon would be hf prime, a different frequency now, plus the kinetic energy expression for the electron itself. This shows you that the frequency of the photon is going to be lower after it has collided with the electron, which makes sense. And since the frequency is going down, that means the wavelength is getting longer. Remember, a longer wavelength means a lower frequency. So the wavelength will also go down. And in fact, we could even calculate what that new wavelength would be, because we would just use the wave equation configured like this, the speed of light divided by the new frequency. would give us the new wavelength of that X-ray photon. So it might seem a little strange thinking of a packet of light changing its frequency and changing its wavelength after being able to collide with something that we've traditionally thought of as a particle, being an electron. But that is in fact what happens, and the observational and experimental data that has been collected only confirms that scientific theory. We can also calculate the Compton shift, which is the shift in wavelength from before the collision to after the collision. So to measure our Compton shift, it's a change in wavelength, which means that it's the final one minus the initial, and that is equal to h, the Planck's constant, divided by the mass of the electron times the speed of light, multiplied by 1 minus cosine of theta, where again, remember from the previous diagram, theta is this angle between the original direction of the photon and the scattered direction of the photon. So what we see here is that all of this in front of our parentheses is a constant value. All of those numbers are constants. So none of that will be able to change. Theta is something that will change based on the situation, and obviously then that will dictate how much your wavelength shifts as the photon scatters off of that electron. Note that the maximum shift would occur when theta equals 180 degrees. That would be when the photon comes in, hits the electron, and bounces exactly straight back off of it, back in the direction that it came from. And also, no change at all will occur if theta is 0, which makes perfect sense because that means that really your photon didn't scatter off anything at all. It just went flying right on by and there was no electron there to truly scatter it, or not close enough to actually scatter it. Note also that in our photoelectric effect that we've talked about yesterday and the Compton effect today, this describes light behaving like a particle, being able to physically collide with another particle, an electron. And that might seem a little bit odd because we also know from our units about a month ago or so that light behaves like a wave because it produces interference and diffraction patterns, which we saw with the laser beam and doing some of those demonstrations in the classroom. So how can light exhibit both qualities of being a wave and also a particle at the same time, and yet that seems to be such opposite cases? However, that exact quality of light, that it can be both a wave and a particle, is really one of the fundamental ideas and one of the strangest mysteries that we have in the quantum physics branch that we're just starting to get into. And yet, even though it's so strange and unknown, it is one of the most significant things that underlies all of these ideas that we're laying out right now, dealing with photons and quantum mechanics and all those sorts of things. So a very strange relationship, but yet one that holds up to be experimentally true. Light is both a particle and a wave, and it can be both at the same time, even in certain cases. That's it for the notes. There really isn't too much today, and I'm only going to add 3 problems to that assignment. So on page 1032, we're going to do numbers 41, 42, and 47, dealing with the Compton effect and that shift in wavelength, and also dealing with that change in energies. Also, please read section 30-5 for Monday. And that will be the section we are covering on Monday. All of the problems for the week, this week's homework, will be due also on Monday, so it is not due today like we would normally do for Fridays. You will hand that in on Monday. So I hope you all have a good weekend, and I will see you back next week.